Differentiability and continuity. Not all functions have a well-defined tangent line at every point. This is not so strange if you think about the definition of the derivative f prime of x equal to limit h going to 0 of f of x plus h minus f of x over h. See, this right side is a limit, so if the left limit and the right limit does not agree, then this limit wouldn't exist, which means that this f prime wouldn't exist. Now, in order to make that more clear, I want to define two limits, the left and right limits of this. So let's write down limit h going to 0 plus f of x plus h minus f of x over h, and also the this is the right limit, sorry, and the left limit, which is f of x plus h minus f of x over h. Now this one is called the right derivative, and this one's called the left derivative. And only if these two limits agree, and if they are finite, then we can say this right side limit does exist, and therefore the derivative does exist. Okay, so maybe I should summarize here. If left derivative is equal to right derivative and they are finite, then it is differentiable. Okay, so that's what I want to say. All right, so that immediately draws our curiosity. When would this thing actually fail? And there's actually a very easy example of such a thing. Consider the absolute value function. Okay, f of x equals to absolute value of x. Do you recall the graph of this? We're supposed to know this graph. The graph of this is this V-shaped thing. And if you look at it on the right side, at any point, the tangent line is just y equal to x. Right? It's the slope on the right side is just 1. Okay? On the left side, the tangent line is -1. At every point, it's a straight line. So if you think about the tangent line, it's just the tangent line. The tangent line overlaps with the graph. However, right here at the origin, you can't really say which is the tangent line. Is it this one or is it that one? What is it? Actually, if you go back and think about the definition of the right derivative and left derivative, the right derivative looks at the right portion of this graph and looks at the derivative, which is this. The tangent line, if you just had the right side, you would say this is the tangent line, right? So the right derivative will be 1. Whereas if you just saw the left side, you'll say that this is the tangent line and the slope of this is -1, and therefore the right derivative is not equal to the left derivative, and you end up figuring out that this is not differentiable at x equal to 0. You can make this argument more rigorous by actually figuring out the limit. So let's try to do that. First, let's think about the f prime of 0. What is f prime of 0? This is limit h going to 0, f of 0 plus h minus f of 0 over h. Now, what is the left derivative then? Left derivative is limit h going to 0 minus of f of 0 plus h is h minus f of 0 over h. But what is f of h? That's like replacing x by h. So you have limit h going to 0 minus of absolute value of h minus absolute value of 0 is 0 over h. And therefore you have limit of h going to 0 minus of absolute value of h over h. Okay, we actually did this limit before, but in case you forgot, let me try to make this argument again. If h is a very small negative value, say negative 0.1. What's the absolute value? This will be positive 0.1, whereas the denominator is negative 0.1. So for any small negative value, the top is always positive, the bottom is always negative, and therefore the fraction gives you a negative because it's plus over minus. And also, because their absolute values are equal, you end up getting negative 1 for any small negative value of h. So as h goes to 0 from the left, this limit will be negative 1. Okay? And in the same way, if I do the right derivative, this is limit h going to 0 plus of h, absolute value over h. I'm skipping these steps because it's going to be the same thing. So if I do this, now h is positive. If it's a small positive value, say 0.1, absolute value of 0.1 is 0.1. It doesn't change. So in this case, it's just h over h. Since absolute values don't do anything at all when h is positive, absolute value of h is same as h, and therefore h over h gives you 1. And as you can see, they do not agree. And so f of x equal to absolute value of x is not differentiable at x equal to 0. Okay, now can we generalize this? Try to think about when this type of non-differentiable points will exist. It will be the case when your right derivative is not the same as the left derivative, and when that happens, that means the graph will have a corner. So think about this case. If you have some kind of a curve here, but at this point you have this left derivative different from the right derivative, what would you have at this point? You're going to have a turn, a sharp turn, which is also called the corner. So if you have a corner in a graph, that point will be a point where the function is not differentiable. Okay, now let me talk about continuity and differentiability. So let's recall what continuity is. What is continuity? Continuity is when you can say the limit of x going to a of f of x is equal to f of a. Okay, if this happens, then we say the graph is continuous. Graphically, there are various ways that this could fail, and you have something like jump discontinuity or removable point of discontinuity, or you may have like functions going to infinity so that the left side is not differentiable. It could also go to negative infinity. Okay, so these are points where the function is not continuous. It is not continuous. Okay, and if you think about the tangent line at these points of discontinuity, you realize almost right away that there's no way you can talk about a tangent line at these points where the function is broken, right? So obviously, we can say that if a function is not continuous, then it is not differentiable. Okay, now, so that's what I want to explain here. So not continuous means not differentiable. Okay. We can actually prove this or explain this more rigorously by using the definition of the derivative. Okay, this time let's use a slightly different form of the derivative. F prime of a equals to limit x going to a of f of x minus f of a over x minus a. This is equivalent to the limit definition using h going to 0. It's just that for our purposes, it's easier to use. Now let's look at what happens to the denominator. This denominator here, if x becomes a, you have what? A minus a, which is 0. So as x goes to a, x minus a goes to 0. The denominator becomes 0. Now, this has an important consequence about the numerator. If the denominator goes to 0 and you still want the entire limit to exist, where should this go to 0? It has to go, where should the numerator go? It has to go to 0, or else the limit wouldn't exist. Okay? So let's think about the following. If limit of x going to a of f of x minus a f of a is not equal to 0, then this limit is a non-zero over 0, so you end up with the limit that does not exist, right? So we're forced to say that in order for this limit to exist, the numerator has to be 0. Okay. All right. So let's try to think about what that means. In order for limit of x going to a of f of x minus f of a to be 0, that means if I move this fa to the other side, you end up with limit of x going to a, f of x equals to f of a. Well, what is this? This is exactly the definition of continuity, right? So we see that for a function to be differentiable, it has to be continuous, and if it's not continuous, then the function will not be differentiable. Okay. So let me summarize this argument here. So if fx is not continuous at x equal to a, then fx is not differentiable. Okay. If fx is differentiable, then fx is continuous at x equal to a. Now, these statements are often misunderstood. Okay? Some people think that, does this mean that if fx is continuous, then it's differentiable? Well, not quite. So actually, let me write this as a warning. Warning. Continuity mean differentiable? No. Why? Because if you think about the absolute value function that we just did, we know that this function is not differentiable at this point, but it is continuous. It's all connected, right? So this is an example where it's continuous but not differentiable. So this is an example where it's continuous but not differentiable. Okay, so you have to be careful. Okay, you actually you have to say that for a function to be differentiable, first it has to be continuous, and then the left and right limits must agree. Now, there is still another case where the function may not be differentiable. So far, we found that a function is not differentiable if if the graph has a corner. B, or if the graph is not continuous. Okay. And in addition to these two cases, we still have another case where the function is not differentiable. Let me explain that by giving you a concrete example. If you draw the graph of y equals to cube root of x, the graph looks like this. And if you look at the tangent line at 0, well, tangent line is like this. Tangent line is the closest straight line that mimics the behavior at a certain point. So if you zoom this part in and made it very large, then it will be really hard to distinguish between this red line and this black curve. Okay, right here, it will be almost the same. Okay, so this red line is indeed the tangent line to this curve, y equals to cube root of x. However, what is the slope of this graph? Well, the slope is undefined because it's a vertical line. So undefined because it's vertical. Okay. You can actually compute the derivative and show that it's undefined. Right now, we haven't reviewed we haven't learned the power rule yet, but later on, if you know the power rule, then you can rewrite this as x to the 1/3 power, and if you differentiate, 1/3 comes down, and you subtract 1 from the 1/3, so it's negative 2/3. And because negative exponents mean 1 over, so it's 1 over 3 times 1 over x 2/3. Okay. So I did something that we're going to learn later, so if you didn't understand this calculation, it's okay. All I want to say is that if you know how to differentiate, then look at this derivative. What is the value of this when x is 0? Well, you have a 0 in the denominator. So what do you get? This is undefined. So this is undefined at x equal to 0. Okay. Therefore, if you have a vertical tangent line, then that's the third case where the function may not be differentiable. Okay. So when you talk about points where a function is not differentiable, you can categorize it in three different cases. Okay. So a function is not differentiable if the graph has a corner, or if it's not continuous, or if it has a vertical tangent.